Welcome. Today we're going to be going over 9.1.4a, and I wanted to give you a couple of hints, and this is probably one of the most important concepts this lesson. And so I wanted to go over what's happening here so that you can understand how to use what you learned from this in order to be able to ace the test and ace the final exam. And so we're going to be talking about how a linear scale factor can significantly affect both the volume, both the original volume and the new volume, and the ratio of volumes of a solid. And so we're going to be talking about this solid. Now, if you couldn't actually cut up and make these figures for the lesson, that's okay. I just wanted to make sure that you understood what to do with it. So if I was to make this into a solid, the base, I'm going to try to make this three-dimensional. Please don't laugh. Okay, laugh if you want. That's okay. So my base, if I want to think about it like this, let's see how this works. So that's this right here. I'm going to call this my base. Not quite sure how easily you can see that. So if this is my base, it's got 3 units this way. That's this. And it's got 4 units this way. So this and this. So this is 3 units. This is 4 units. And then what I want to do is I want to be able to represent how big it gets. So let me see how it works with this. So I see that it goes up 2 units here. So I'm going to go up by 2 units. And again, this might be a little bit hard to visualize to begin with. So kind of bear with me, see what happens. So that's this right here. And then, so really this is this one right here. This surface is this surface. So I went up by 2 units. The base itself was 3 by 4. And so same thing as here, 4 units. And then here. So here we have the top of the object. And so again, it might be hard to see, might be hard to visualize, but what we end up with, let me kind of try to make a clean copy, is this object. And what we're trying to do is figure out the volume, the original volume, and then if we dilate it or make it bigger, we want to figure out the new volume. So if I were to fold this net up, I would end up with this cube and this cube. So we have the side here. We have the top. Let's do this for the side. Oh, that's dark. Oh, well. Live and learn, right? So, and then we have, here's the top. So for this object, what we want to do is we want to kind of think about it in little pieces. So here, it says that we've been talking about surface area and volume, and those are the key concepts for this chapter. And so today, what we're doing is we're going to be describing what happens when we fold that up. What do we get? So I'm going to leave that for you to describe, but I'm going to go ahead and talk about the dimensions. So I already wrote them here. This is 3, this is 4, and it goes up by 2 units. So I might call this my length of 3 units, my width is 4 units, and my height is 2 units. That's the way I chose to build it. Your units might be, it might be that you had the height 4 and the width 3, but as long as you have these 3 numbers between these 3 boxes, you should be good. All right, so now on the lesson, it asks you to go ahead and build a bunch of these where we make it bigger by a scale factor of 2 and 3 and 4. And you also have the original, which is really teeny tiny when you try to build it. But let's just say that you didn't have the supplies to actually cut up these things and build these boxes. And that's okay. If you didn't, you didn't, and nobody's going to get upset if you could not personally build it. That's all right. But we are going to talk about what happens when we do build it. Now, this all goes back to the Cubeville videos. If you have not looked at the Cubeville videos, you really should, because the Cubeville videos, while mostly just there to amuse you, are also there to help you to understand what happens when you take a single cube, which is pretty much what I do in those videos. We take a single cube and we say, well, what's going to happen if I take that cube and if it gets 5 times bigger? If it gets 5 times bigger, it gets 5 times bigger in 3 different dimensions, length and width and height. And so what I end up doing is I end up taking a cube 5 times the size of the original, and I start filling it up. And it literally takes me 13 videos to fill that cube up. And it would not take me 13 videos to fill the cube up if it was just 5 times bigger, because then I'd only need 5 videos. Or why would I need 13? Now 13 is sort of a random number, but it's definitely more than 5. And that's because it's going to take more than 5 of these in order for you to be able to build the new cube. So what we're going to do is we're going to kind of take what the Cubeville videos teach and what this lesson is teaching and kind of put them all together. So this right here is really the big kahuna of this lesson. So let's first figure out what the original volume is. And this number is going to be the same no matter what, because we're all starting with this object. So if I want to figure out the volume of this object, the first thing I need to do is figure out how many cubes are there on the bottom layer. Now, because I decided that this was my base, in order to figure out how many cubes, I could literally count the squares, or I could say, well, it's really 4 times 3. In my base, it's going to be 12 units squared. Or if I want to talk about cubes, it's 12 cubes. And then I have to say, well, how many layers do I have? Well, I have 2 layers. So if there are 12 cubes on my first layer and 12 cubes on my second layer, my volume is going to be 24. And we're just going to go ahead and use units. So the units are cubed. Units are always cubed for volume, and this is a big deal. So units are cubed. And so my original volume is not going to change no matter what I do to make a new object. So I'm just going to go ahead and write this number, cubed, 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 all those spaces, because that number does not change. Now what I need to do is think about what happens when I make it bigger. And I've got this lovely graph paper, so I'm going to see if I can use this to draw a picture of what it looks like when it's bigger. So if I make it bigger, my new dimensions, if my scale factor, well, first, if I multiply every one of these dimensions, every one of these by this scale factor, 1 times 3 is 3, 1 times 4 is 4, 1 times 2 is 2. So my volume, if I just make something the exact same size, is the exact same volume. So that's with the scale factor of 1. So when I have a scale factor of 1, I'm going to make a ratio of those volumes. So if I take the original, that's this one, 24 units cubed, over my new volume, which is 24 units cubed. Now the instruction says, what is the ratio of the volumes? Which is really not very useful. I mean, it's useful, but so what I'm going to do is I'm going to simplify my ratio as much as possible. I still want it to be written as a ratio, which means I want it to be a fraction, but I'm going to go ahead and simplify. So the units are identical, top and bottom, so they cancel, they're gone. And then 24 goes into itself once, and 24 goes into itself once. This is the ratio of the volumes, and it's what I would expect. If I take two objects that are the exact same volume, and I make a fraction of those volumes, I'm going to get 1 over 1. Simple. But we're going to use these numbers to figure out the complicated answer we're going to get for the bottom line of this table. So now what I want to do is I want to kind of help you to picture what happens with my object when we're talking about a scale factor of 2. So if the scale factor was 2, then that means that instead of this being a, let's see if we can, so instead of this being a 3 by 2, I'm going to multiply everything by 2. So it's going to be a 6 by 4. All right? So I'm going to go ahead and draw this here. So I'm going to go across by 6 and then down by 4. I do not know if I'll have enough room on this piece of graph paper, but we'll give it a try. So the original, and this kind of shows you something. My original was 3 by 2. But when I increase the actual dimensions, so this is doubled, it was 3, now it's 6. This is doubled, it was 2, now it's 4. You'll see that the area of just this one surface is not just double what the original. The original was 2 times 3, or 6 units squared. But this is going to be 6 times 4, or 24. So that's going to make a huge difference. And so that's something that we want to keep in mind. Now the next thing we want to do is we want to look at this dimension. So this is a 2 by 4. So it's going to be a 4 by 8. And I think I'm going to barely have enough room on this graph pad, which is good. So originally I had 2 by 4. So this was the original dimensions for that flap. That's this top flap, the one that I labeled as a 6. So these are the original dimensions of this side flap. Now the big base here, instead of being 3 by 4, is going to be 6 by 8. So this is 6 and this is 8, so this is my new base. And so now 6 times 8 is no longer 12, it's 48. So the original, well, I'll just draw it down here. So if this was the original base was 12, the new base is 48. This flap was originally 6, but the new base is 24. And this was 8, but the new one is 4 times 8 is 32. So hopefully you're starting to see a pattern here. We made the object twice as big, but each of these shapes is not twice as big. It's actually 4 times as big. And so let's see if we can figure out how that's going to affect the volume. So I'm going to keep going. This bottom one is a 2 by 3. So instead of 2 by 3, it's going to be 4 by 6. So this is the original 6, and the new one is going to be 24. So we've got these surfaces. So we've got the original shape. This is where we would normally fold it to make our new picture. And then what we want to do is we've got 2 more surfaces. So this one is going to be 4 by 8, because originally it was 2 by 4. So originally it was 8, and now it's 32. And then we have this one, which was 3 by 4. Now it's going to be 6 by 8. And I am really lucky to make this fit, because I did not know it would fit on this paper. Obviously, I'm not going to build this the bigger ones. But what I wanted to do was kind of give you a way to picture what's going on. So here is my other base. So let me finish drawing the outline of the original net so you can see what's going on. So here's my object. And so I want to figure out the new volume. Now the way I found this volume of the original was really to take 3, which was this dimension, times 4. Those are the dimensions of the base. And I multiplied them by the height. So my base is now here, 6 times 8, so that's the 48. And then I have to multiply that by the height, which is this distance, which is 4. So if I take 48 times 4, that's going to, because now I have 4 layers, and every layer has 48 blocks in it. So 4 times 48, let's see, 4, let's see, 32, and 4 times 4 is 6, so that's 192 units cubed. Now let's take a look at what this really means. What I really ended up doing was multiplying each of these numbers by my scale factor 2. When I did that, 3 times 2 was 6, so I'll just put that word here. 4 times 2 is 8, and 2 times 2 is 4, so 6 times 8 is 48, times 4 is 192. So all I really had to do was multiply each of the length, the width, and the height by the scale factor. So I ended up with this. So now what I'm going to do is make a ratio. So my ratio begins with my original over my new volume, which is 192 units cubed. The units will cancel. And then I'm going to discover that 24 goes into itself once. 24 goes into 192 8 times. Now, let's take a look. We multiplied 2 here, and 2 here, and 2 here. What's 2 times 2 times 2? That's this 2, and there's 3 dimensions because length and width and height. So 2 times 2 times 2 is 8. So our ratio from the original to the new one, the new volume is 8 times the size as the original, and that 8 comes from the fact that we take 2 times 2 times 2. So now let's use that information to try to figure out what's going to happen on this next one. So now my original volume was 3 times 4 times 2. That's really what I ended up doing to get my volume. But now I have to multiply each number by 3. So if I multiply that by 3, I get 9. If I multiply this by 3, I get 12. And if I multiply that by 3, I get 6. So now I'm going to take 9 times 12 times 6, and I'm going to go ahead and use a calculator because I know I'll mess it up otherwise. So I'm going to take 9 times 2, 9 times 12 times 6. And we're going to start to get some really big numbers here because what we're doing really makes a huge difference. So suddenly my new volume, if I wanted to build this out of blocks, I would need 648 blocks just to make it. Now if I take this 648 and I divide it, so I take 24 and I want to find out how many times it goes into 648, I'm going to discover that it goes into it. It's going to be an interesting number. Let's look. So if I take 24 units cubed divided by 648 units cubed, the units cancel. 24 goes into itself once. 24, if I take 648 divided by 24, I discover it's 27. Now that 27 is really multiplying each of these dimensions by 3, because 3 times 3 times 3 is 27. So if I make the dimensions bigger by a unit of 3 on each, for each length and width and height, then the new object is going to be 27 times bigger. That's like huge. So now let's see if we can figure it out for the next one. So this next one, basically we're going to take the original length, which is 3, times 4, that's 12. We're going to take the original width, which is 4, times 4 is 16, times the original height, which is 2, times 4 is 8. When we multiply those numbers together, let's see what we get. 12 times 16 times 8. Now we get 1,536 units cubed. And so I kind of dare you to try to figure out what you think this bottom number is going to be. If I take 24 units cubed divided by 1,536 units cubed, the only thing I have to do to really figure out what this is say, well, all I'm really doing to figure out how much bigger it is, I'm taking this number and that's being multiplied 3 times. So 4 times 4 times 4 is 64. So you can check my work. Take 1,536 divided by 24. And what you're going to discover is 24 goes into that number 64 times. So here, when we're looking at our new volume is our old volume times our scale factor. Length times our scale factor, and our width, which in this case is 4, times our scale factor. We don't know what the R stands for, we just know it's a number, times our height, times our scale factor. Because this is the new height, the new width, and the new length. And so what we get is 3 times 4 times 2 is 24, and R times R times R. So 24 units cubed, and then our new one is going to be 24 times R cubed units cubed. So the units cancel, the 24s cancel, and what we end up is discovering that the difference is the scale factor cubed. Now think about it, whenever we're talking about the volume, the units are cubed. If I want to make something that's 5 times as big, what I have to do is take my scale factor, which is 5, I'm going to cube it, which is 5 times 5 times 5, and that number I'm going to multiply it times the volume of the original. So if my original, because in Cubeville, each of the original cubes was exactly 1 cube, 1 unit cube, 1 times 1 times 1. But then in Cubeville, I had to fill a cube 5 times as big, which meant that I had to multiply this one by 5, this one by 5, and this one by 5. So 5 times 5 times 5, I needed to build 125 cubes to fill in a cube 5 times as large as that original. And that's key because on your test, you're going to be asked to discover what is the new volume and surface area of an object when the linear scale factor is 5 or 12 or 2,978. So that's kind of your big hint and tip for 9.1.4a. Thank you.